All right, my friends, in this video lesson, what we're going to talk about is, first of all, this term enthalpy, and then we're going to get into a little bit more about energy and kind of how it works through a chemical reaction, okay? So first of all, when you're talking about thermodynamics and this idea of heat, the word enthalpy comes up a lot. And it's kind of just a fancy word for heat is really what it is. You can actually interchange those things if you want to. But if you're looking into a science world, what people talk about is the enthalpy of a system or the enthalpy change. Really what they're saying is what is the heat change or what's the heat content of that system. That's kind of what enthalpy is. Now, enthalpy is always affected anytime you have a chemical change, always, all right? Some physical processes also have enthalpy changes or heat changes to them, okay? For example, dissolving things into water. Sometimes when you dissolve things in water, we see a heat change or a change in energy because of that dissolving process, okay? Not always, but sometimes we do. And it's enough that we should actually talk about it. The symbol that we use for enthalpy is the delta H, okay? So it's a change in heat is what we're calling this, okay? So enthalpy really is measuring the change that happens over a reaction. So it's the change in our heat or change in our enthalpy, okay? When we work with enthalpy, we actually have it across lots of different things. So here in the pink box, we're talking about all the different ways enthalpy can change in the chemistry world. We can have fusion, which is just the melting process. We can have freezing, we can have boiling, we can have condensing. They're all just heat changes, but we use a different subscript for the different things or a different sign to represent what is happening for that enthalpy change, okay? Chemical reactions have an enthalpy change. We just call that the heat of a reaction. When you dissolve things into solution, they have an enthalpy change. We call that a heat of solution, okay? And then finally, if you're going to actually form compounds from their elements, there's actually a standard to that. So what would be the heat change to take, let's say, pure sodium and pure chlorine and make sodium chloride from it, okay? That's called a standard formation. So that little knot symbol there is that standardized symbol for us for that one, okay? The biggest thing is as we go through this unit, when you see the word enthalpy, just kind of keep in mind that we're talking about the heat change or the energy change first off. And we'll use the word heat and enthalpy pretty interchangeably, okay? Now, as we take a look at this idea of changing heat or enthalpy or changing our energy states, we need to talk about something called bond energy, or basically the energy stored in a chemical bond, all right? If we have chemical bonds, these bonds store a little bit of energy for us, and they kind of hold it there as potential energy as we're looking at these chemical bonds. Now this graphic is here to kind of help us visualize what's going on. So the bond energy is this space between, our bottom point and here. The bottom of the trough is representing the space at number 3 where the actual chemical bond has been formed, okay? We're going to start over here at number 1 and kind of talk about the process of forming a chemical bond. If you have two separate atoms that are not close to each other, they're both going to be at a high energy state. That's an unstable state. As they come closer to each other, as we see in number 2, what happens is their energy decreases, okay? So they are actually losing energy at this point, okay? So they're losing energy as they get closer to each other. They'll continue to lose energy until they hit a minimum point. At that minimum point, that's the perfect location where the attractive forces between the protons of one atom and the electrons of the other atom balance out the repulsive forces of the protons of the two nuclei, okay? So there is a kind of a perfect distance apart that every bond makes, okay? We call those bond lengths, and we actually studied those in trimester 1, okay? So this perfect bond length represents the lowest point of energy for this chemical bond. If you try to force them to get closer to each other, we see a sweeping very quickly rise in energy again because that repulsive force of the two nuclei would not like that. So it repels them back. As a result, we end up getting chemicals that end up having this perfect distance apart at their lowest energy state. Okay, we call that the chemical bond. Right? So this is where they are bonded together. Anything too close and energy goes up. Anything too far away and energy goes up. So the perfect point is kind of like at the trough of this, at the very bottom. Kind of like imagine dropping a marble in here. It's going to go back and forth, back and forth, back and forth, back and forth until it stabilizes at the bottom of the trough where it's most stable. That point is called the bond energy, okay? And that bond energy is represented as a negative value because we set the original to 0, okay? So there's actually a loss of energy to form those bonds, okay? That stored energy that comes from this formation of the bond is potential energy, so kind of what we have. So the question kind of arises then, okay, so if this is losing energy, where does the energy go? Because we know that from our law of conservation of energy, energy can't be created or destroyed, so the energy has to go someplace. So we're going to kind of talk about that next. To do that, we have to kind of take this idea of what is going on and talk about what's happening for our chemical bonds. So number one, when we have a change during a chemical reaction, energy is always put in to break chemical bonds. Okay? So what we saw previously on this, we saw bonds forming, so energy was being taken, was releasing. When you're going to break a chemical bond, you have to put energy in. So if we go back to this, if we're down here and we have a chemical bond, if we want to break this, we have to pull them apart, which means we have to make them run this direction up the curve, and we'd have to put energy in to separate them, okay? You always put energy in to separate them, and when they form, they always go down. Okay, so these two things are kind of always is for us. Energy is always put in to break chemical bonds, and then once they're broke, energy is released when they make new bonds, okay? There's a comparison because there's a certain amount of energy it takes to break the bonds and a certain amount released when they make new ones. So the comparison between the starting point and the end point tells us if that chemical reaction is going to increase energy overall or decrease energy overall. If it releases energy overall, it's going to be considered an exothermic reaction. If it absorbs energy overall, it's going to be considered an endothermic reaction. Okay? Now, ultimately, for elements and compounds, they want to have the lowest bond energy they possibly can. They want to be at their most stable state, which is the least amount of energy present there. So everything kind of wants to go to low energy if possible, because that's their more stable and the preferred position for these elements. Okay? The next couple of slides we're going to take, we're actually going to show a combination of both breaking and forming bonds onto a single graph. Okay, so let's first talk about an exothermic scenario. Okay, we call these energy diagrams because we're diagramming out where energy is and how it changes. Again, we have potential energy on our y-axis because we're measuring the potential energy that's available in the system. Here's our system. We have hydrogen reacting with oxygen to make water. Okay. At the beginning of our system, the combined bond energy of hydrogen and oxygen is going to be at this potential energy level, okay? To get these to break apart, we have to put energy in. We always put energy in to break things. So we have to increase the energy. See how the curve goes up? Okay? It's very much like going back here, how this curve would go up. So we're increasing energy to get those bonds to break. This increase in energy, we call that the energy of activation, or sometimes just the activation energy. All reactions, this is a great time we can say all reactions require energy input to get them to react. These are these energies of activation, all of them, all that happen, okay? Once they're broken, then after we break all these apart, we form the new bonds into water. So as you forming new bonds, we see a drop in energy, okay? So forming these new bonds is releasing the energy. So we had to put energy in to break, we release energy to form the new bonds, and then water ends up having its new baseline of a potential energy. Now if you look, we had this much energy before, and now we have this much energy. So some of the energy left, okay? So where does it go? Well, that's where we actually can see the energy going into our solution or going into the physical mass of our substance. All of this is about bonds and electrons inside the atoms, okay? If we have energy that leaves, it goes into the actual solution. It goes into the thermometer that's measuring this temperature. It goes into the environment around it. So as exothermic reactions run, they're releasing heat energy, which means it warms up everything around it. That's why exothermic reactions become warmer as they run on their own, okay? Not because we're warming them up, because they're running on their own. They will get warmer on their own without any sources of heat to make that happen, okay? Overall, if we take a look at our energy change here, between the two things, we had energy go up first and then down afterwards. So we have a negative energy change as our net result, okay? That's important to note because a negative energy change is also a way to identify an exothermic reaction, because negative means you're releasing energy as you're going through there. So this negative is a way for us to measure out that we're losing energy here, okay? If we flip the process, let's say we start with water, and now we want the water to break apart and become hydrogen oxygen. So notice how we have a double-headed arrow. We actually can run this in reverse. It's the exact same scenario, except for everything just gets reversed or flipped. So we first have to put a bunch of energy in to break the water bonds. And then once you form the oxygen and hydrogen, it's going to reduce back down again because it always loses energy to make new bonds. Here, our energy change is going to be a positive overall change because we went from low to high, which means that we have to put some energy in, okay? Well, where does the energy come from? Again, it comes from the environment. If we're not using any type of thing like a cooling mechanism or a refrigerator or a freezing thing, and all we're doing is letting this reaction run at room temperature, it has to pull energy in from someplace. Usually, it pulls the heat energy in from the molecules around it, so it makes things colder around it, okay? Otherwise, it could pull it in from electricity as energy, could pull in UV light as energy, other sources too. But typically we see that endothermic reactions, when they run, they tend to make the things around them colder because they're pulling energy away from those external things in there, okay? So usually we say that exothermic reactions warm up on their own and endothermic reactions cool down on their own, okay? Again, the key there is on their own. It's not with a source of heat that we are providing, like a Bunsen burner, or a source of reducing temperature like a refrigerator, okay? Now, all of that information leads us down this line of how do we actually calculate the energy change that happens in a chemical reaction, okay? So our next video is going to go into that, about what are thermochemical equations and how can we start putting numbers to these energy changes that happen during a chemical process. Thank you.